Hello everyone, I am Noor Alam, PhD student, Department of Electronic Engineering, Kwangwon University. Today I will present a research topics entitled Dynamic Growth Monitoring of Saccharomyces cerevisiae based on microwave sensor array. In this work, basically focused on Saccharomyces cerevisiae OIPH 4999, a strain widely used in fermentation and biotechnology. Although yeast is studied extensively, real-time monitoring of its colony growth on solid media is still very limited. Most current techniques rely on optical imaging, microscopy, or electrical measurement, and they typically require manual handling, expensive equipment, or liquid culture. This creates a job gap for applications where we want a non-contact continuous monitoring approach that works directly on agar. Agar-based assays are extremely useful because they allow many colonies to be screened at once and preserve their natural morphology. If we can track their growth without disturbing the plate, we gain a much more accurate picture of proliferation. Traditionally, people use optical methods, microscopy, or electrical sensing. All these approaches have limitations. Many require liquid culture, meaning the colony morphology is lost. Others depend on expensive instrument and skilled professionals. During period of high demand, reagent and supplies can be difficult to obtain. For remote or resource limited areas, these systems are hard to scale. All of these motivates a simpler, more accessible sensing methods. Here Fig 2 shows actual image of microwave monitoring system. To develop an NSRR based microwave sensor array capable of monitoring yeast growth continuously with 9 resonators, it can extract multi-frequency and multi-parameter signals. Then it can be used PCA and Dempster-Shafer evidence theory for data fusion. The key idea is that yeast growth affects dielectric properties that leads to measurable changes in resonant frequency, insertion loss, FSI, and FWHM. Finally, build a mapping between a synthetic microwave parameter MSP3 and biological indicators such as survival and apoptosis rates. NSSR, NSRR structure design. The sensor is based on nested split ring resonator design. The nested rings increase capacitance without increasing the footprint, which allows multiple resonant frequencies across LS and C bands. Each of 9 resonators RM1 to RM9 operates independently. The electric field is strongest near the ring gap, which make these the optimal sensing zones. Here Fig 3 shows actual image of NSRR array. The vertical field depth is enough to cover the full colony thickness throughout the growth cycle. This ensures high sensitivity during all stages of proliferation. proliferation. For the experiment, OIPD agar was prepared and aligned on top of the NSRR array. Each droplet were placed above each resonator. and the entire assembly was scaled and incubated. A vector network analyzer continuously recorded the microwave spectrum. To confirm resonator independence, a simple water droplet tested. Only the loaded resonator showed spectral changes, and the other remain stable. This verifies that all 9 channels operate independently and can track different colonies simultaneously. Yeast growth can be divided into 4 phases: lag, log, stable, and decline. Each phase produce distinct dielectric responses. These changes are important because they help us link microwave measurement to biological behavior. Here, Fig 5 represents schematics of yeast growth microwave monitoring system, microwave parameter variation app map এবং MSP3. Looking at the resonance parameter, we see that resonance frequency decrease initially and then increase as the colony matures. The insertion loss S21 follows a similar pattern, fast dropping and then recovering. These changes are associated with budding, membrane variation, and colony thickness. To model the growth, here a applied a logistics curve to all parameters from Rm on to Rm9. The R square values vary depending on the resonator and parameter. In general, non-resonant parameter gives smoother fits. Then used PCA to combine the data across all 9 resonators. The first principal component PC1 captures most of the variance, ranging from about 51% to almost 100% depending on the parameter. PC1 consistently achieved higher R square than any individual resonators, showing that the sensor array performs better than single array sensing. Here we look at the full spectrum. We see clear signature corresponding to 4 growth phases. Using DS evidence theory, generated multiple synthetic parameters MSP1 through MSP9. Among them, MSP3 showed the strongest relationship with yeast viability. The mapping between MSP3 and the biological survivable and apoptosis rates achieved R square of 0.9985, which means that the fit was extremely accurate. This allows to evaluate fermentation performance in real time. Here, Fig 8 presents logistic growth curves of Saccharomyces cerevisiae based on 4 microwave parameter and its fitting R2 heat map. Here we summarize the logistic fits for del F, del S21, FSI and FWHM. Again, the R square values vary across resonators, but PC1 captures the majority of useful information. About 88% for del F, 51% for del S21, and more than 99% for FSI and FWHM. This confirms PC1 can be served as a strong composite parameter. When applied to the first 3 growth periods, PC1 gives better logistics fitting than any individual resonator. To validate the microwave results, biologically we used here methylene blue used staining and processed the images with binaryization and the thresholding to obtain live and dead cell counts. Both live and dead cell numbers increased over time but at different rates, which produce the classic H-shaped trend of yeast growth. From this data, we calculate the survival rates NS and apoptosis rate eta A. The average for each period serves as ground truth for our mapping with the microwave parameters. For measurements, data measurements from 4 time point for 1927 and 63 hours, covering all growth stages using DS evidence theory. Here, fuse the probability distributions of 4 microwave parameters to generate MSP1 to MSP9. After after comparison, MSP3 was selected as the optimal synthetic parameter. Its relationship with survival and apoptosis is very strong. Again, with R square equal 0.9985. This confirms MSP3 is highly reliable for accessing yeast viability from microwave data. In this summary, the NSRR sensor array provides a powerful platform for real-time monitoring of yeast on solid media. By combining multiple resonator and multiple parameters, significantly improve accuracy, MSP3 emerges as a strong indicator for yeast viability and can support application in brewing and microbial quality control. Looking ahead, future or could explore microwave effects on cell psychology, optimize sensor fabrication, and improve scalability for industrial use. I'd like to thank all of the authors for this research paper published in ACS Sensor. Thank you everyone for your kind attention.